Okay, good morning again, everybody. So today we're going to continue the topic of derivatives, and our main discussion today is going to be L'Hopital's theorem. But before that, we have a few leftovers from last time. So let me remind you the definition that we saw actually at the very beginning of the semester. A point, x0, is called a local minimum or a local maximum, respectively, if the value of f at any other point x is greater than or equal to the value of that x0, for every x in a neighborhood of x0. When we have, so these are the two definitions of local minimum and local maximum, and a local minimum or a local maximum are called local extremum. Okay, so that's the definition. And we've seen the following facts. I'm not going to write them in full detail because this is really stuff that we've seen. So we know if f is differentiable, meaning it has a derivative at a local extremum. So if you have a point which is a local extremum and f is differentiable there, then the derivative is 0. This is what? Right. This is precisely Fermat's theorem. So this is one thing we know. And we know that this is not an if and only if statement in any sense. So the converse, bless you, the converse is false. And the example that we mentioned, but there are of course many others, is the function x cubed at 0. So the function x cubed does not have an extremum at 0. It's not a minimum or a maximum. However, the derivative is 0. Okay, at x0 equals 0. Okay? And another thing that we've already seen, so I'm continuing the we know statements, an extremum could be a point where f is not even differentiable. So an example for that, which again we already mentioned, would be the function absolute value, which has a minimum at 0, but it's not differentiable there. So finding it in terms of finding the derivative and setting it equal to 0 will not locate this point. Okay, so here's a new one we didn't write on the board here yet. x0 will be called a critical point if it's suspicious in the sense that it might be a local minimum or maximum. So it will be called a critical point if either the derivative is 0, that makes it suspicious. It doesn't determine that it's a local minimum or a local maximum, but it makes it suspicious. Or f is not differentiable at x0. Okay, so that would be the definition of a critical point. And now we have two theorems that help us determine or classify such critical points. Okay, so let me maybe, okay, I'll write the theorem and then I'll draw a little picture. So the first theorem is called the first derivative test. The first derivative test. And it says the following: let x0 be a critical point of f, and assume that f is continuous in a neighborhood of x0, continuous and different. Sorry. Sorry. Let me correct this. Where's the thingy? No thingy. 1 second. Luckily, I have a new thingy here. Okay. So assume that f is continuous at x0 and differentiable in a neighborhood of x0, possibly not at x0 itself. So these seem like little details. They're needed for the proof. So it would be easiest to just assume that it's continuous and differentiable in a neighborhood of x0. You need it to be continuous at the point, obviously. You don't need it to be differentiable at the point, but you need it to be differentiable in a neighborhood. So that's kind of the setup in order to use this theorem. But once we have all these assumptions, then, so I'll continue it here. If f prime, which we assume exists in a neighborhood of x0, if f prime changes signs from minus to plus at x0, then x0 is a local minimum. And if f prime changes signs from plus to minus at x0, then x0 is a local maximum. A local minimum, a local maximum. And if it doesn't change signs, if f prime does not change signs at x0, then x0 is not an extremum. So here's the picture. So here's a function. Functions are blue. Here's a function. And suppose we have a critical point and we want to decide whether it's a minimum or a maximum. So we're assuming the function is differentiable in a neighborhood. If this point is going to be a maximum, then on its left, the function is going to be increasing, and on its right, the function is going to be decreasing. Do you agree? So maybe I will indicate that by doing something like this, right? How is that reflected in terms of the derivative? On its left, the derivative is going to be positive. That's the theorem we ended with last time. And on its right, the derivative is going to be negative. So that's this statement. If f prime changes signs from plus to minus at x0, then x0 is a local maximum. Clear? And of course, vice versa, or the other situation, if it's a local minimum, then the function is going to be decreasing and then increasing, and therefore the derivative is going to change signs from being negative to being positive, and then it's going to be a local minimum. Clear? And the last situation that can occur is the situation of x cubed, if you can still have the derivative be 0, but be positive on both sides, like in this situation. And this is precisely the case where f does not change sign, f prime does not change signs, and therefore it's not an extreme. Okay? Do you agree with the statement of this theorem? Okay. So here we have f prime positive in all this region. Okay, so that's the first derivative test. It's very useful because all you have to check is the first derivative. That's why it's called that. Its let's say drawback is the fact that you need to check the first derivative on an interval. You don't just check the first derivative at the point. There it's going to be 0. That's how you found the point, right? Or it might be a cusp. You need to check it in a neighborhood. You need to check what happens to the first derivative on points to the right, points to the left. So in that sense, you need to do some work in order to use it. Okay? The second derivative test, so theorem, second derivative test, is slightly different. So the intuition, maybe let's look at this board again. The intuition for the second derivative test is the following. Suppose you have your f prime, and it changes from plus to minus. Okay, f prime changes from plus to minus. So what the second derivative test is going to say, that you can kind of see that in terms of the second derivative. What I'm going to say now is just intuition. It's not accurate. So if the second derivative at the point is positive, if the second derivative is positive, that indicates that the first derivative is increasing, right? When a derivative is positive, the function is increasing. So if the second derivative is positive, the first derivative is increasing. Do you agree? So if the first derivative is increasing, and you know it was 0 here, then it must have been negative here and positive here. Or that would be for this point. Do you agree? So let me write that. Let x0 be a critical point, and assume that f is twice differentiable at x0. So here I'm really only looking at the point itself. Then, if f prime prime at x0, the second derivative, is positive, that means that f prime is increasing. If it was 0 at the point, it must have been negative and then positive. And that means that x0 is a local minimum. right? Negative and then positive, yeah. And then if f prime prime at x0 is negative, this is just intuition. Actually, the formal proofs of these two theorems are not hard. They're rather straightforward, but I'm not going to write the full proofs. Then x0 is a local max. And if f prime prime at x0 is 0, we don't know. We don't know in the sense that the second derivative test fails. It doesn't tell you whether it's a minimum or a maximum or an extremum at all. All three cases could happen. Okay? So let's just write one or two examples. So if you look at so example 1, look at f of x equals x to the power 4. X to the power 4, do you know what the graph looks like? Right, it's kind of a, yeah, good, flattened parabola. I like that. Good. So it's kind of a, sort of like a parabola. So the first derivative is 4x cubed, right? So the second derivative is what? 12x squared. At 0, the second derivative is 0. Does everybody agree? So let me write that. F prime prime at 0 is 0. Okay, so it's this situation, and we don't know, in this case, what's 0? It's a minimum, right? If you look, on the other hand, at x cubed, and if you take minus x to the power 4, it would be a maximum, right? Satisfies still this, but it would be a maximum. And if you take x cubed, the first derivative is 3x squared. The second derivative is 6x. It's still satisfied that f prime prime at 0 is 0. And in this case, it's not an extremum at all. So all situations can happen when the derivative at the point is 0. Okay? And let me just say this. I'm not going to write this. There are derivative tests of higher order. So when this happens, you could move on to a third derivative test and classify according to the third derivative. And that would have kind of a dichotomy like this, but a situation where it fails, and then you must move to a higher order. I'm not going to even phrase higher order derivative tests. Just know that they exist, and if you need them, you can look them up in the literature. Okay, so we're never going to need anything beyond the second derivative test. Yes?
What's the difference from the first and the second?
They're different in nature. Well, first of all, the first one only tells you check the first derivative. Okay? But it tells you check the first derivative on an interval. Okay? And according to that, well, we discussed it a bit. According to that, you can determine what's going on. Sometimes. Okay? Here, you just need to check the second derivative at the point. Okay? At the point itself. Okay? But it might fail. Okay? And of course, if the function is not twice differentiable, of course you can't even use this. And there are always examples that you always need to apply the theorems that are relevant and that are legal to apply. Okay? Okay. Good. So this kind of wraps up the discussion of these derivative tests of sorts. 1 second. I want to mention one more result. We will get back to studying functions. Okay, we still didn't do the full story. There's still the issue of concavity and inflection points and asymptotes, and we will get back to that. but that would be later this week. One more result that I want to mention really briefly. I'm not going to discuss too much, but it's important to know, is the following. So we know that if you take a function and it's differentiable, we prove that it must be continuous. Remember? So any differentiable function is continuous. That does not mean, and that's a common mistake, that does not mean that the derivative itself, f prime, is also continuous. Okay? F prime, the existence of f prime implies that f is continuous. But it doesn't imply that f prime is continuous, and that could not happen. And here's a very short discussion of this situation. So the first theorem is called Darboux's theorem. Darboux, a French mathematician. And it's sometimes called the intermediate value theorem for derivatives. We had an intermediate value theorem for continuous functions. This is sometimes called the intermediate value functions for derivatives. It says the following: let f be differentiable on a closed interval. By this I mean that it's differentiable at any point, at any inner point of the interval, and on A it has f prime plus at A and f prime minus at B. Okay, so it only has one-sided derivatives at the endpoints, because that's all we can discuss. Okay, maybe I'll write that. Exist f prime plus at A and f prime minus at B. That's what I mean by being differentiable on a closed interval. And let C be a value, any value, bless you, between the values at the endpoints, f prime plus at A and f prime minus at B. And the intermediate value theorem in this sense says that then there exists a value, an x value, x0, such that the derivative at x0 is precisely that c. So f prime at x0 equals c. So any value between the values of the derivative at the endpoints must be attained at some point on the interval. Okay, so do you see that this is a sort of intermediate value theorem? It's just for the derivative. Yep. Okay, and a corollary of this, which is what we're really interested in, is the following. If f is differentiable on, let's say, AB, on a closed interval, then it may have points of discontinuity. No, then f prime, f itself may not have points of discontinuity, because if f is differentiable, then it's continuous. But f prime may have points of discontinuity. F prime need not be continuous, but only, remember, we had three kinds of points of discontinuity. We had jumps, we had removables, and we had essential or oscillating or infinite. We had various names for these third kind, okay? But only essential. Ones. So a derivative can never have a jump discontinuity. And let me argue this, wave my hands to argue this really quickly. Look at the derivative at f prime. It's some function. If it has either a removable discontinuity or a jump discontinuity, it's not going to satisfy the intermediate value theorem for derivatives. All the values in between are not necessarily going to be attained. Do you see that? Okay? So the only form of discontinuity that it might have is an essential discontinuity. And when you think of an essential discontinuity, you might think of either an infinite one, where you'd still attain all the values in between, but not, not in a continuous way, or a sine 1 over x kind of thing. You still attain all the values, but it's still not continuous. Okay? So that's really, really a very short discussion of this phenomenon. And maybe I'll give you one example, but it's not trivial to understand this example. I'll write it down. If we have some time later, maybe we'll get back to it. Let me write one example. This example is a very good exercise. Very good exercise. It's not hard in terms of calculations. You have to understand what you need to do. So, example, look at the function f of x equals absolute value of x to the power 3 over 2 times sine of 1 over x. So this is defined whenever x is not 0, and at 0, just define it to be 0. Okay, so I wanted to take x to the power 3 halves times sine of 1 over x, but I can't take roots of negative numbers, so I put it in absolute value. Okay? And this function, the claim about this function is that show, this is a homework problem, that f prime is not continuous at x equals 0. So you need to find f prime first. Okay? Finding f prime at any x which is not 0 is rather easy. There's a product and a little chain rule here, right? For x is positive and x is negatives, that's easy. Do you agree? Finding f prime at 0, you have to use the definition of the derivative. You have to take the limit as x approaches 0 of f of x minus f of 0 divided by x minus 0. That's in order to find the derivative at the point 0. Okay? And then you get a function. You get the function f prime. Show that that function is not continuous at 0. It's not even going to be bounded at 0. It's going to be an essential discontinuity. Okay? Very good exercise. Okay, but I won't spend time and do it in full detail here. I highly recommend trying this. Okay. Questions on all of this before we move to l'hôpital? Yes?
Yes, on the last score, I didn't understand.
The statement is, take a function. Assume it's differentiable on the interval. We know that it's continuous, right? Because differentiability implies continuity. But this discusses the continuity of the derivative, not of the function. The statement is, the derivative is not necessarily continuous. That example shows you that a derivative need not be continuous. Okay? But this theorem says that if it has points of discontinuity, okay, they're not going to be removable and they're not going to be jumps. They're only going to be essential discontinuities.
And that's the reason the theorem still holds.
Yes, Yes, you can, that example shows you that. You can see on that example, if you work out the details, there's a bit of work here. Very good practice work. This is a great question for the final. I like it. Okay, good question for the final. Try this. No, seriously, try this. This is very good practice because you need to understand what you're doing. You need to understand what it means to finding the derivative by definition at the point 0 and y. And how do you check continuity of f prime? Okay, there's understanding in order to work out the details of this thing. What you will find is that f is differentiable. F prime at 0 does exist. But f prime is not continuous at 0. In fact, it's not bounded near 0. It has an essential discontinuity at 0. Okay? Okay. So now we're moving on to our... I wanted to make one more tiny remark. Remember last time we discussed again Lagrange's theorem, and we mentioned Cauchy's theorem, and so apparently, first of all, these theorems are sometimes called the mean value theorems. And the second remark is that the attribution to Lagrange is not a consensus. So some people actually attribute Lagrange's theorem to other mathematicians, including to Cauchy. So I don't know. I've always learned it as Lagrange's theorem, so I called it Lagrange's theorem. Lagrange was a great mathematician and scientist. He did lots of other stuff as well, but maybe he just got credit for something that he didn't do. Who cares? No, I think that people care a lot about attributing correctly their triumphs, but I may have made a mistake, but that's okay. It's not on purpose. Okay, so our next theorem, attributed to L'Hôpital, another French mathematician, L'Hôpital's rule. Okay, so before I write the actual theorem, this is what we're going to discuss from now until the end of the lecture today. Before I write the actual theorem, I want to discuss kind of do an overview, discuss the story. So L'Hôpital's rule is actually, this is a bunch, not one, a bunch of theorems. A bunch of theorems, very similar to each other, that allow us under certain conditions that we always have to verify, right? Whenever we apply a theorem, we have to verify that its conditions hold. But when the conditions hold, these theorems allow us to calculate limits. And not just any limits, the most annoying limits, limits of the form, what we called infinity over infinity, or 0 over 0, right? So these are the limits that limit arithmetic doesn't work for, and we had to always work harder, right? And these theorems allow us to calculate these sort of limits in all the various situations. So when either x goes to a, or x goes to a plus or a minus, or x goes to infinity or to minus infinity, all these situations, that's why it's a bunch of theorems. And how do they allow it? So, answer, in some cases, under these conditions, the limit of f of x over g of x whether x goes to infinity or to a plus or a minus. This is the limit we want to calculate. And it's a limit of the form 0 over 0 or infinity over infinity. Meaning either both f and g go to 0 or both f and g go to infinity. In some cases, this limit equals the limit, let's write x equals a. This limit equals the limit of the quotient of the derivatives. Not the quotient rule. I'm not taking the derivative of the quotient, which would be, remember, f prime g minus g prime f over g squared. I'm just taking the quotient of the derivatives. What we would wish would be the quotient rule for derivatives, but it's not. Okay? And in some cases, namely these conditions, they're equal. And moreover, sometimes this is much easier to calculate. If that's the case, and this is easy to calculate, then we know this. Okay? Let me give you, before we even write the theorem itself, let me give you a couple of examples to show you why this could be useful. Now, life in general is divided into two parts. Life in general is divided into two parts. Before you know L'Hôpital and after you know L'Hôpital. Why? Because this is such a gem that after you learn it, you tend to just apply it all the time. To the extent that we're going to learn how to apply it even to situations which are not of the form f over g. Okay? And you just, you see a limit, boom, you hit it with L'Hôpital no matter what. Okay? And we'll see in examples that sometimes that's not such a good idea. Sometimes it's good to remember your life, your pre-life, before you learned L'Hôpital, and to put L'Hôpital aside. Okay? So, okay, examples. First of all, some positive examples, why I say that this is a gem. So, here's our first example. We're going to see many examples today. Example 1. Let's look at the limit as x goes to 0 of sine of x over x. Remember how hard we worked in order to calculate this? We did some geometry and pictures and used the sandwich theorem. Remember this? We worked hard to prove this. What do I mean hard? Half an hour of lots of drawings and calculations. Remember? Yeah. L'Hôpital. So I'm going to write here LH, standing for L'Hôpital. This is a L'Hôpital 0 over 0. Okay, so this would be my code for saying I'm using L'Hôpital's rule in the 0 over 0 situation, right? When x goes to 0, this goes to 0, and this goes to 0. Do you agree? Now, I'm not telling you the conditions for L'Hôpital's theorem yet, but they're going to easily hold here. Okay? So you're going to believe me that it's legitimate to use the theorem here. What do I get? I get the limit, x goes to 0, of the derivative of sine, which is cosine, divided by the derivative of x, which is 1. And this limit is 1. Unfair. Yep. That's why I'm saying there's life before L'Hôpital and after. Do you agree that this is almost free, especially compared to how hard we worked previously? Okay. Here's another example, which you can try doing without L'Hôpital. Might be a bit challenging. So, for example, the limit is x goes to 1, ln of x divided by x minus 1. Okay, so this is an 0 over 0 situation. So it's still going to be L'Hôpital 0 over 0. Do you agree? And all I'm going to do is take the limit, x goes to 1. The derivative of ln of x is 1 over x. The derivative of x minus 1 is 1. Limit is 1. Good? Questions? Hmm? How to do this without L'Hôpital? Try. Sometimes it's to the extent that it's too difficult. Okay? Sometimes, we'll see many examples. We'll see many examples today. I just want to emphasize one thing. The word lim and the word ln tend to be, over time, tend to reduce to this. Right? But it's important to put the point up here, the dot, when you want to say lim. So when you don't say lim, it's clear that it's ln. Good? Okay. Yeah, you're allowed to giggle. Okay. Questions about this? So let's write, and of course, make sure when you use L'Hôpital not to use the product rule, the quotient rule for derivatives. But take the derivative of the top divided by the derivative of the bottom. Let's write the full statement of L'Hôpital's theorem. The full statement of the theorem. So theorem, let f and g be differentiable near x equals a. Near means in a neighborhood of x equals a. And I'm going to again emphasize that possibly not at a itself. And this is important. This is very important because we're calculating limits. And for limits, the functions can even be not defined at the point a. Okay, so we need the differentiability in the neighborhood. That's where we're taking the derivatives. But it could be a punctured neighborhood. The functions can even not be defined at a itself. Okay? Assume that. So the assume that is going to be what I called previously the conditions of the theorem. This is the things we have to check. So the first condition is the obvious one, that the limit of f of x as x approaches a equals the limit of g of x as x approaches a equals 0. So remember we said this is a bunch of theorems. I'm writing the first one. Okay? So here we assume that we're in the 0 over 0 situation. Both f and g go to 0. And I'm going to be interested in the limit of the quotient. Okay? Everybody with me? Okay, good. The second condition is a slightly more technical one, saying that the derivative of g is not 0 in, let's say, for all x which are not a, near a. So we're dividing by g prime. We must assume that g prime is not 0. It could be 0 at the point a. At the point a, we don't care what's going on. We're just discussing limits. Okay? And the third condition, again an obvious one if you want to apply this theorem, is that the limit of the quotient of the derivatives has to exist.
The third one doesn't imply the second one? The third one doesn't need the second one to happen for...
No. And then, so this is the assertion of the theorem. So if everything here holds, then the limit of the quotient of the original functions coincides with the limit of the quotient of their derivatives. Okay? Now, remember we said this is a bunch of theorems, so I just wrote one of them. Let me write all the other ones. And instead of writing this 15 times, I'm going to write all the other ones by telling you what you can change. So, for example, this 0 could be infinity. That would be the second theorem. Okay? Or actually, it could be plus or minus infinity. It could be infinity, or it could be minus infinity.
Couldn't one of them be infinity and the other minus infinity?
Could one be infinity and the other minus infinity? That doesn't make any difference. You just pull out the minus and you get infinity over infinity.
So they don't have to be equal then?
No, if they're not, it won't be a direct application of the theorem. You just pull out the minus from one of them, and then you do have it, and then you apply the theorem.
Yeah.
Okay, so it doesn't matter. So that's one thing. The other thing is that this point A here, as we said, could be A plus or minus, or plus minus infinity. So you have bx goes to infinity, x goes to minus infinity, x goes to a plus, and x goes to a minus. Of course, you'd have to modify things here respectively. So if you're requesting, if a is infinity, you need it to be differentiable in an interval of the form from some alpha to infinity. Okay, you need to modify things. And when we say exists here, remember we said that usually when we say exists, we mean it exists in the strict sense. It's a finite. But in this theorem, everything is good. Finite or plus minus infinity. All work. Okay? So for any combination of these, you get a different theorem. And all of them together are called L'Hopital's rule. Okay? Yes?
On the first one, when we said positive and minus infinity, it's always possible to play with it and to get it.
Let's do many examples. Okay? More questions after the examples. You'll see all kinds of situations that we can handle with this. Okay? If it's still not clear afterwards, I'm not going to erase this throughout the lecture. It's going to stay on the board. Let's see many examples. Let's see, first of all, two examples that we already did. So do you agree here that this is, here it goes to a point? Both functions f and g have limit 0 when you approach that point. Do you agree? So that's condition 1. It's satisfied. Do you agree? Condition 3, saying that the limit of the quotient of the derivatives exists, we actually check that after we finish the calculation. That's this statement, that this limit exists and we found it, right? So when we first write this, it's kind of a conditional equal sign. It will only be equal once we prove that this really exists, right? And after we finish this, that justifies this equal sign. That's condition 3, saying that the limit of the quotient of the derivatives exists. Do you agree? And the second condition, saying that the derivative is not 0 in a neighborhood, it's obviously satisfied here, and likewise for this example. Okay? So the one thing that's kind of an agreement between us when we write it like this is that this equal sign only becomes valid after we finished our calculation. That was when we actually verified the third condition. We write this as we work, but we must keep in mind that it's really only a truth, only valid once we actually got to the end. Clear? Let's do many more examples in order to demonstrate all the different situations that, oh, time for a break. Okay, so let's have a break here, and we'll do more examples after the break. Okay, so 10 minutes break.